engine in a distributed fashion to compute tables. First, of course, set up the way of distributing it and the table parameters. And finally, bring together all these tables to whoever wants to show this to be insecure, or preferably even keep them distributed and only collaboratively ever break packets. So to keep it a public proof of concept rather than a one-person exploit tool. Now, as I was saying, most of this is already done. We did implement a number cruncher on graphics cards, and we did compute the best possible way of using known rainbow table and distinguished point techniques to generate tables from those. And I would like to ask a couple of you at least to download this right now, so we have at least a few mirrors. I don't know when I'll get the first email to take this down, but I want this to be spreading as soon as possible. And now here's where you get involved. We need computational resources to compute these tables. We don't want to do it in any central location, and preferably we don't want anybody to ever have all the tables, but of course that's up to you. We need specifically CUDA graphics cards, that is NVIDIA graphics cards, or we need FPGAs, that's a more specialized type of hardware, much more efficient though still. Now, quick poll, how many gamers are in the room with a good NVIDIA graphics adapter? Yeah, okay. That could almost do it already. We need a couple of dozen, preferably around 80 if we want to be done by the end of the year. So that's a good start. Go ahead, download the software. I'll, for the rest of the next half an hour or so, be talking about how we've been optimizing this engine and how we have been computing these table parameters. The basic message, though, is on this slide. Go ahead and help us compute the tables. Now, a little bit of cryptographic background. What technique are we using to break this cipher? We're using, as I was saying, a technique that doesn't even exploit the statistical weaknesses of the cipher, but rather a generic technique. That's why this might be interesting for you too if you want to break other ciphers with small key sizes. 64 bits seems around the limit that you can be pushing. So we are looking at a codebook computation attack, where a codebook is a mapping from all the outputs back to the secret information that went in the first place to compute these outputs. So in the case of a stream cipher, that is the secret state. If you know the secret state, you can compute the key stream that comes out of it that is used to encrypt an entire voice call or a text message. So we want a mapping from the output that we see going over the air back to the secret information that went in generating this. And now imagine you had a book, like a phone book, where it's ordered by the output and it points out to you the secret state that was in it. All you need to do once you see something flowing over the air is look up that information and you get the secret state. Easy enough, right? Codebook attack. Now there's two limitations we need to overcome to make this practical. First of all, this codebook, even though A51 uses a small key, is still 128 petabytes, which might be more than storage available on Earth, at least more than we'll ever get together for this project. So we need one way of compressing this codebook to store it more efficiently. Another limitation is if we just went ahead and computed this with Intel processors, it would take us a combined 100,000 years, probably much more even, depending on the optimizations we can do. So we also need to make it faster. Even among all of us, we don't want to spend 100,000 computing years on this. And that's the two optimizations I'll be briefly talking about that make this practical. So to make the computation much faster, we did a couple of things that differ for the platform this is being computed on. For the CUDA card, we maximize the number of parallel instances we can run on this existing processor. Unlike an Intel processor, where now you have something like 2 cores, maybe 4 in server processors, a CUDA gives you a couple of 100 cores, each of which can be used to crunch its own A51 computation. So right there you get 100 times or more speed up. On FPGAs, you can parallelize even more. You're very flexible. In FPGAs, you're not talking about the number of cores, but rather But resources you can just puzzle together to form whatever you want. And if it's small enough, you can use many parallel instances, thousands in fact, on a good vertex FPGA these days. So that gives us a couple hundred to 1,000 times speed up. Then the next optimization, the next layer of the optimization we did is on the CUDA graphics card, try to utilize the available resources, especially SRAM in this case, as much as possible to parallelize the computation as is. So to jump ahead a couple of computation steps. In this case, we had a 4 times speed improvement through that alone. So instead of 240, we only need 80 CUDA cards now. On an FPGA, the optimizations are a little different since the clocking rate is variable. You get more speed from simplicity. It's a beautiful design goal to have it as simple as possible, to be as fast as possible. We don't really have that in software anymore much. So that's the different layers of optimization. And we reach a very achievable goal of spending 3 computational months on 80 computing nodes. Any of your gaming machines will do, or on about 20 mid-range vertex processors. So if anybody has FPGA resources, we'll be more than happy to use those too. Let me just do one deep dive into the technical details. The source code is available, so any questions should be answered through that. But let me do one deep dive into how we did the 4 times speed up on the CUDA card, which might be interesting to you just to see the different trade-offs of the CUDA as compared to either FPGAs or CPUs. So the A51 algorithm has 64 bits in its state, split across 3 different registers. Each of these registers may shift 1 over in every clock, and then the empty slot on the left needs to be filled, of course. Now, a simple implementation of this would compute, based on all the 64 bits, which 3 bits need to be shifted in, and then shift 1 over, move those in. That is slow. Shifts are extremely slow in software, and CUDA is, for the most part, a software-driven system. So if there was any way of computing several such shifts at once, it would speed it up significantly. Now, it turns out that only a subset of the bits in the state of these 64 bits is needed to compute what is coming next. So in this case, only the bits, the state bits in the boxes are needed to compute the next 4 shifts, right? So what we do is have lookup tables in the very fast SRAM that basically comes for free. So one clock cycle access to look up those next 4 bits that come in. The exact way this is being looked up is shown here for one example. And so just going through these lookups will give us the next 4 shifts, and we get a 4 times speed up since the shifts are really the bottleneck. That's just as one design optimization, or an example of which, where you now use the free SRAM for speed up. On the FPGA, we do similar tweaks to keep it as simple as possible and maximizing the throughput. Now, are there any questions so far as to the implementation? I know this is kind of, for some of you, very interesting. For others, you're like, oh, let's get to the table computation. We want to get going. But are there any questions, or can we leave that behind us? Okay. So table computation. What I'll be discussing now is several techniques out of the domain of pre-computation attacks, these codebook attacks, right? We already said the simplest possible codebook is not going to fit on any possible hard disk, even though we now have the resources of generating the data. We can't possibly store them. So what we're doing is we're storing them compressed, you could say. And here's how. Instead of only saving storing input values and output values from one computation, we do